How does it compare?
Well, I don't know. Individual things could make things very difficult for a thesis. Well, yeah, but less completion. So there's a balance there. But I think so that's we can all discuss this, right? What is the scoping? That's the key question. What's the right scoping?
I had, but I think the first round is pretty good. Because the second round was pretty good. I did not do it because I started actually, right? So.
Okay, why is that looking at me? It's up to you.
Yeah.
He's running like a lab.
I know. The advisor can really go wrong. Otherwise, you cannot offload these kinds of things on the advisor. You have to make those editorial decisions as well, push back and maybe tell everyone that maybe not yet. There's no advisor can really figure out your challenge.
That's awesome.
So it's not three.
Yeah, so that one gets long enough like fly out there. But it's like it's a startup, so they have asking like technical questions really, or like the technical program questions. And they just figure out the meeting project. Yeah, so.
How long is it?
They use it as like kind of small project, like all this fish. I think so. Do you have any plans? Okay, cool. That's Seattle.
Yeah, it's in well, it's in it's called
So they're like Spokane. They have. Is it 3 hours east?
Yeah, it's like 3 hours east, just southeast.
It's like the middle of that.
Yeah, pretty much. It's in the middle of there.
Well, it's nice up there. It's really hot.
Yeah, I don't know.
During the summer, like Seattle's super nice. I think Eastern Washington is like pretty hot. It's like 4 hot. There's a river.
Yeah,
I think there's a bunch of like river coffee and stuff out there.
Oh, really?
Or a bunch of like
They said that they know like all that, but this
I don't know.
paddleboard?
Yeah,
Yeah, that's cool.
like meeting with my team and like he goes in like in my like these kinds of stuff. I told him that I'm not interested. I'm interested in this channel, so now you have to try to make this. One that I make them.
Yeah.
In the I don't want to stand up. Everybody would be included by that.
All right. Let's start. So, I wanted to sort of wrap up a few overall, sort of an overview of the things we talked about last couple of lectures on fingerprinting. So, we talked about how you can use this idea of converting a problem you're trying to solve into some kind of polynomial testing. And then it turned out that using some randomness, you could very quickly check with a high degree of accuracy whether the problem you're trying to solve, can be solved or not, depending on the problem. Right? So we looked at very different kind of things, try to verify that a matrix multiplication is in fact correct, trying to communicate information between two entities, or even try to do things like spine with a graph as a perfect matching. And in all these cases, there was some amount of randomness, but if you didn't realize it was showing up in different places, right? So in the first case, when you were doing matrix multiplication verification, this AB equal to C idea, What we had was, and this is true in all cases, you have some kind of polynomial you construct it over some field of values, and you evaluate the polynomial at some point in that field, right? And the trick is how you do all of these things. So in the first case, when we said we want to check AB equal to C, what we said was treat this as a polynomial evaluation problem. AB equal to C is a very simple polynomial, but it can be more general. And then evaluate it at a random point in the field. So you have a field, which you chosen arbitrarily, you have a polynomial that's given to you by the problem, evaluate a random point in the field, and because of, if the thing you're checking is low degree, then the probability of you incorrectly concluding that something was true when it's not true, that AB equal to C when it was not, would be very small. It's basically the ratio of the degree of the polynomial to the size of the field you're working over. Right, and so that's what, so the randomness there came from evaluation of the, where you choose to evaluate the polynomial. Okay. When we talked about fingerprinting though, when we said, okay, we have these like bits of numbers, Alice has a bit string and Bob has a bit string, and we want to compare them, we said, okay, treat this as an integer by basically using the base 2 representation of the number, and then take it and then compute the number modulo a prime number, some kind of random prime number. But if you're doing something modulo a random prime, what you're basically saying is you're picking the field at random. Right? The field that you're working over is being picked at random, and that's what you're doing with fingerprinting. Okay? And so that's another way to introduce randomness into the testing process, not by evaluating at a particular point, which you kind of are implicitly doing by saying evaluate it at the value 2, because you're saying, you know, sigma ai 2 to the I. Right? So you're saying evaluate at 2, which is fixed, but evaluate is holding over a random field, do this model over a random field. And of course, there's always a polynomial involved in this. And what we didn't see, you know, that's why I marked it there, is some cases where you don't actually, you're not doing a specific computation, so you can choose what polynomial you want to compute, and you can choose that at random. And it turns out, you know, when you look at things like hashing, which we won't cover right now in this course anyway, what hashing boils down to is picking a random polynomial and evaluating your input at the random polynomial, and then getting a value from it. So instead of evaluating a fixed polynomial and doing it modulo a random prime number, you're evaluating it with respect to a random polynomial. And that gives you something like hashing. So in all these cases, there's something you're doing with the polynomial. Either you're choosing a random polynomial or a random field to evaluate over or a random point to evaluate on. And then the process of analyzing an algorithm and looking at the probability of an error gives you what you want. Okay, so again, this area starts getting a lot bigger and a lot more complex as you sort of go further. This goes well beyond these 3 cases. So again, this is merely to give you kind of a teaser of what is it that you can do with randomness and polynomial testing. Okay. Yeah. Okay. So are there any sort of questions about last time's material and this sort of comment I'm making here? We're going to sort of move away from randomness at this point to other topics, but this is the last thing I just wanted to point out. Okay. One thing I will say though, that this whole business of evaluating at random points is a lot more powerful than it looks, because there are a lot of problems now, like I said, where the goal is to essentially, someone gives you an answer and you want to check if the answer is correct. So you want to verify something, and the verification process in some sense has to be random. And when you do it in this randomized random evaluation, you can check that things are correct without ever having to actually compute them. And there's a formal way in which all this can be said, which if you ever took a class in complexity theory, we would sort of talk more a little bit about this. Okay. So if there are no more questions, we're going to sort of move away from randomness, at least for a while. We might come back, but we'll move away. And again, I want to take this chance to sort of pick up a level, look at sort of the bird's eye view of where we are so far, what we've done, where we're going next, and how all these things fit together. Okay. So let's see. So far, again, we've talked about, again, just to repeat, we've talked about basic design tools, right? We looked at some slightly more advanced tools, things like network flows. And we looked at even more advanced tools using randomness. And all of these, there was some sense of, when you could try to apply this in homework 4, of course, you're trying to do this with network flows, and we will soon see sort of how to play with randomness to achieve certain goals that you want. Randomness is a bit more complex topic, so you won't get that same sense of, okay, I know where I can apply randomness that you do with the others, but it's a start. And especially when you come to something like network flows, there's a sense of translation from one language to another. In other words, we're taking some problem that could be anything, and we're insisting, no, there's a way to express it in the language of network flows, in the language of edges and capacities and flows and sources and sinks and variations thereof. And this is, of course, a strange thing, as you're all probably dealing with right now. It's kind of a struggle to sort of figure out, exactly how this is supposed to work out. And it takes some effort to translate from one language to another. This comes up here, it'll come up when we talk about NP hardness. But in general, this idea that you can take your problem and convert it into a different entire framework with its own structure, and then forget about the original problem essentially, right? It's a very powerful tool in what we do. And what we're going to start talking about now is a much more general version of this. So you can think of network flows as a very specific example of a much more general framework to do this. The whole general framework of what we would call optimization. And just like with network flows, right, there are two parts to thinking about optimization. It's basically how you express a problem in the language of optimization, and then how you solve such problems. We'll probably spend a lot more time looking at the first part of this, how do you translate a problem in the language of optimization. We'll spend much less time looking at the second part, how do you actually solve these things, because that's a whole other, in fact, there are a couple of courses at the U that are taught about how to do optimization in MATLAB. Maybe some of you have already taken them or plan to take them as well. And so that's what I want to start by talking about today. And of course, if you need any further motivation to study this, there is at least a sense in which all of machine learning is optimization. Why? Because you take some problem, you translate it into some format, it becomes what we'll see as an optimization problem, and then you solve it. And so the central effort is getting it into that sort of format where you can apply some optimization effort to it. So that's one more reason that you want to think about this. But of course, it's a very general framework for solving any kind of problem. So what is an optimization problem? So an optimization problem has basically three components to it. So the first component are variables. These are unknowns, things you're searching for, right? So you want to find your max flow on a graph. The variables are the flows you're going to place on every edge. But these are the basic things. And of course, since you're optimizing, there's the thing that you want to optimize for, which we'll usually call an objective function. So I want to find the maximum flow. What is the maximum flow? Well, it's the sum of all the flows and all the edges coming out of the source. Okay, so I have my variables, which are the flows. I have my objective, which is the sum of all the flow coming out of the source. And you want to either maximize or minimize this objective. But the thing that makes all of this tricky, right? So if you have variables, so if I have one variable, and I have some objective function, and I want to optimize it, this you've been studying since high school, right? This is basic calculus. How do you maximize a function? So I give you the function f of x is equal to x squared. It's defined over the range 0 to 1. Find the maximum value of x squared over this range. You do some calculus, differentiate, you find the extreme points of range. It's all good. You can do all those things, right? It's a continuous function. So discrete functions is a bit harder, but you can do something similar. What of course makes this tricky for both discrete functions and also in continuous case is that you have constraints. All the flow coming into the vertex has to equal all the flow coming out of the vertex. Because what constraints do is they sort of tell you, no, this solution you're proposing for me is not a valid solution. This other solution is not a valid solution. You have to maximize, but only in the space of valid, feasible solutions. So all your calculus kind of breaks down now, because sort of just basic ordinary differential calculus doesn't allow you to really say, oh, I have to differentiate with keeping in mind all these constraints, right? Because if you have to say, okay, I have this function, I want to find the maximum value, but it has to be on the unit circle. That's a different problem to solve than just saying, I have this function, I want to find this maximum value. And sometimes you can use calculus, depending on how the constraints are defined, but more often than not, you cannot do. And so any optimization function involves these three things. And typically, depending on how these things are defined, you get different kinds of optimization problems that are more or less easy to solve. So you'll take a problem, you'll take some problem, and you'll map it to this setting here, and then we'll try to solve it. So let's take, before we go any further, let's just take some examples of problems we may have even seen before. So let's take a simple problem. So let's say we have a problem which we'll call a scheduling problem, right? And we have let's define some basic terminology. We have M machines, we have N jobs, and each job, so job I has duration, let's say Ti. Okay? And my goal is to let me just write. Schedule jobs on machines so that all jobs finish. Well, not all jobs finish. All machines end work as soon as possible. So if even one machine is still running, you're still waiting. You can't leave the machines unattended. So you want to wait till they're all done, then you can leave. So you want to make sure that essentially the worst case, the machine that's the slowest or that's doing the most work ends as soon as possible. So this is a problem, right? And now I can say, okay, I should be able to write this as an optimization problem. To do that, you have to ask yourself all these questions. What are the variables? What's your objective function? And what are the constraints? And of course, what you will find is that depending on how you set up the problem, you might end up with a different optimization problem. There are different ways to choose an optimization problem depending on what your goal is. In this case, the problem is pretty well defined. I've essentially written down an optimization problem in English. So it shouldn't be too hard to convert. But in more general case settings, you may not see this, right? So, for example, some of you know that I work in this area called algorithmic fairness, where you want to do decision making that's fair for different groups. So your objective function is to be fair, but who knows what that means? Different people have very different ideas of what that means. That would change your optimization. And as a separate issue, that can have all kinds of unintended consequences. Okay, but we'll get to that. So if I have this problem, how do I frame it as an optimization? Well, what I want to do is say, okay, what are my variables? What are my objectives? What are my constraints? Right? So what are the variables here? What are the things that you will need to figure out to provide any solution to this problem, let alone a sort of a good solution? What are the variables here? The unknowns in a scheduling problem. What is the space you're searching for?
You don't know how much work each job is going to take.
Well, we do, because each job has duration Ti.
Oh, okay.
And you can assume all machines process each job the same way. So it's not like the same job in two different machines will run differently. Although that's another problem that people study as well.
The starting point of the job, that's not mentioned. I mean, is it the same?
Well, the point is every machine can run exactly one job at one time. So I run a job, it's done. The next one, that's done. Next one.
That means we have a set of jobs already.
Well, that's my input, right?
Yeah.
That's what I specified. I'm giving you any job, and the job is very.
So you're
Well,
unknown.
1 second. So you're yeah.
Well, I was going to say, you don't know which job has to run on which machine.
You don't know which job has to run on which machine. So that clearly is the space of choices you're searching over. So if I had to express the notion that a job is run on a machine, I have to encode that as a variable somehow. So how might I do that? How do I encode as a variable the decision about which job is to run on which machine? Right?
You just write as a matrix of n cross m.
But okay, but what is the entry for that?
So each row should have only one of the.
No, you're putting constraints. What are the variables? Yeah.
You could write Java I runs on machine J.
That's a statement. How do I express it as a variable? I need a variable that encodes that choice. Yes?
In like a graph in machines and jobs
Yeah.
and an edge directed at.
You want an edge? I still want a variable. I don't want an edge or something. But we are very close. I mean, this idea of an edge, all these things are correct-ish. They're right in the right space. I just want you to nail that final statement here.
Something like a tuple.
Huh?
If it's a variable, you can have a set of tuples.
Say more.
One job with a corresponding machine.
Yeah.
And a tuple. And
What does that tuple consist of? For a
a
job
with
and a
its
machine.
corresponding machine.
Right, but a tuple has many things in it. So when you say a job and a machine is a tuple, what are the things in the tuple?
An array of tuples, so a set of jobs, each job with a corresponding machine.
So all of what you're saying is that you somehow have to decide which job is going to go on which machine. So maybe the easiest way to do this is to have a variable, call it xij, which encodes the idea So you have a variable xij. If xij is 1, then we have decided to put job I on machine j. If it's 0, we haven't. If I did some searching and I found descriptions for all of these things, this would presumably be the way in which I would then solve that problem. I have encoded a potential solution to this problem in the language of variables. Right? Okay. If I have these variables, can I write down an objective function? Can I write down a function that captures this goal I have, that all machines should end their work as soon as possible? Which is another way of saying that I want the worst case running time for a machine to be as little as possible. But to do that, I need to know what the running time for a machine actually is. All I'm allowed to use are these variables. How do I express the running time of a machine in the language of these variables? What will it be? How do I measure how long the machine takes? So I fix any machine you want, right? How long will it take to run the jobs in the machine? Yes?
It will be xij into ti.
It will be xij into ti. So it'll be something like, well, that's just the time it takes to run job I on machine j.
So it will be for all n jobs summation.
So that the time that machine j takes is equal to the sum over all jobs 1 to n of ti xij. So why does this work? If the job I was assigned to machine j, that number will be 1 and I will pay the time ti. If that job I was not assigned to machine j, that will be 0, I will not pay any time. So this is the time machine j takes. Now how do I express the idea that I want, all machines to finish as quickly as possible? Right? What does that mean? This is a single value. What is the minimum of a single value? Maybe you're something.
Correct. Yeah.
Say it more. You're almost there.
Min-max.
Min-max. You're just three words. Throw more words.
Max over all machines time.
Right.
And we want to minimize min over I.
So you can see now the object. So the worst machine, the machine that's going to spend the worst amount of time, is the machine that will take max. So let's call this time for j, right? So this will be the worst machine, right? This is the time that the worst machine will take, right? And now we want to minimize. Right. Okay, good. So what have we done so far? We've got our variables. We've got our objectives. But we also have constraints. To figure out what constraints we need, we should look at the variables we have. So the variables already encode a kind of constraint that the value is either 1 or 0. Okay, so we should say that explicitly. Look, every variable has to be either 1 or 0. Right? Because we are saying that we want to use 1 as a proxy for choosing and 0 as a proxy for not. But there's no way to tell our variable, hey, you have to be 1 or 0. So we have to incorporate that as a constraint. So we say that xij belongs to 1 and 0. What else do we have to say? What other constraints do we need to make sure that we have some kind of sanity check?
No job is being done on more than one machine. So
No job is being done on more than one machine. How would you write that constraint down, given what the variables you are allowed to have? So we have this idea, no job can be done on more than one machine. Good. How do we say that in the language of these variables? Use any function you want. What would it say?
Sigma j
Sorry?
sigma j xij equal
Okay. So one constraint we're going to say is that sigma j xij is equal to 1. This basically says no job can run on more than one machine. Okay? All right. I have a solution to this problem, and it works for every possible input. Oh, I see. No. Equal to 1. No, I don't have a solution. I used to have a solution. I don't have a solution. Okay, good. Is there anything else we need?
Can this be a constraint, like the machine shouldn't be idle between running two jobs?
Do you care? But do you care? No. I'm asking a question.
Oh.
The answer is not okay. The answer is do you care?
Do you care? Okay.
Suppose the machine is idle. What will happen? Do you get an illegal answer?
Illegal?
You get an answer that's not feasible. You get an answer that's bad.
Yeah, I do get.
Okay, but that's what our objective is supposed to do. Our constraints are supposed to make sure that we don't get answers that are illegal. Our objective will make sure we get answers that are good. So you're worried about it not being good. If you start saying machines should be idle, right, then you're imposing some judgment on what a good solution should look like. That may be true, but you don't need to worry about that just yet. That may be something you have to worry about later. Maybe you write this way, it doesn't give you a good answer. You say, okay, maybe I should add some extra constraints because I know that every good solution must have this problem. But that's not something we need to worry about right now. Right? Are there any other constraints we need? So one way now to check to say, okay, is this a sufficient number of constraints? Is to say, can we now prove that we get what we want? That a solution of a certain, that the solution we get there is a solution we get here and so on. Right? So I think by construction it's clear that if we have a solution to the scheduling problem, right, where all the jobs are completed at time t, then if you plug in that particular assignment, you said xij equal to 1 appropriately, this will clearly be true. This will be true because you only put one job somewhere. And then this min-max will be equal to that value t. So that part is easy, right? If you had a solution there, you have a solution here. But just like we saw with the flow stuff, what about the other way around? Suppose if I look at this question here, I have taken away all information about where the problem came from. All I have are these variables, xij, which are 1 or 0. That interpretation is not part of my optimization. That's what I think it should look like. It's just a variable that's 1 or 0. And in fact, it's just this. I have this quantity here, and I want to do this. I don't know anything about where this problem came from. It's just some arbitrary scheduling problem, arbitrary optimization problem. If I have a solution to this optimization problem, can we be sure that we can convert it into a solution to our actual scheduling problem? So we get some solution, right? We know from the first constraint that all values are 1 or 0. That's good. That means there is a specific choice you're making. We know from the second constraint that since summation of xij is 1, and all xij's are equal to 1 or 0, that means for every I, there exists exactly one j. So given a solution to the optimization, right, which will be basically a set of values xij, right? We know that for all I, there exists exactly one j, we'll call it j of I, such that x I j of I is equal to 1. So we assign job I to machine j. So given a solution to the optimization, we can read off the rules it's giving us as to how to assign jobs to machines. Notice that ordering doesn't matter in any of this because you're just putting the machines in jobs in one by one. You just want to minimize this stuff. And because we have this function, which is the optimization function, we know that when we run this, right, the time it will take for those jobs to run the machine is exactly given by this and this min-max. So our constraints have allowed us to make sure that a solution to one problem gives a solution to the other problem and so on. So this is a valid optimization that will solve your issue. Okay? Any optimization process, no matter how complicated, looks like this. You have some problem, you want to model it as an optimization, you figure out what your variables are, you figure out what the objective is, you figure out what the constraints are, and you write the whole thing down. Okay? So, in general, any kind of optimization objective can be written as minimize or maximize. Notice that if I have a minimization problem, I can maximize just by flipping the sign of what I'm optimizing. Minimize over some variables x1 through xn, some function of x1 through xn, subject to constraints of the form gi of x1 through xn is less than equal to 0 or equal to 0 or greater than equal to 0. Again, so if you want to be particular about this, and this can actually matter for some problems. You have two kinds of constraints, less than equal to constraints and equal to constraints. These are slightly different. So any optimization problem eventually looks like this. And the good thing is that if we can take a whole bunch of different problems and write them in this generic form like this, then we can forget where the problems came from and just figure out how to solve this problem in an abstract form. Not surprisingly, some versions of this will be easier than other versions. There's a whole taxonomy of problems. And so the skill as an optimizer is knowing which kinds of optimizations are easier to solve than others, and then trying to figure out for your problem whether you can translate into a particular optimization form which is easier to work with. So for example, let's go back to our scheduling problem for a second. The constraints are, this is one constraint that's called the discreteness constraint, that xij is either 1 or 0. That has some issues with it. This constraint is what is called a linear constraint. It's a linear function of the variables. So it's a different kind of constraint. It's an equality constraint. And then you have this objective, which is a min and a max. So it turns out you can write this in a different way, where you don't have a min and max. For various reasons, a min-max double constraint can be hard to optimize, because you're maximizing negative over two things, right? Because you're maximizing over here you're maximizing over j, but you're minimizing over all xij, right? That's kind of hard to do. You can take the same optimization and rewrite it. So how would you rewrite this optimization? Well, you can do something like this. So let's rewrite the scheduling we can take the objective and make it a constraint. So let's say the following. So once again, we have the usual constraints. So we have, xij belongs to 0, 1. Summation over all j xij is equal to 1. And now I'm going to write a new constraint. Summation over all I ti, sorry, tixij is less than equal to t, where t is some brand new variable. And then I say subject to that, I want to minimize t. So what I've done is I've added one new variable, which is t. And what I've done is I've changed my, I've done something to my objective. So the question is, how does this compare to the previous one, which looked like this? So look like this. So the difference is, again, we have one new variable, we have one new constraint, and we have a modified objective function. I claim these solve the same problem. But what does it mean? What is happening here is that I'm saying, look, I want to minimize the max, but the max value has a property, by being the max, that everything is less than it. So if I knew what that objective value was, let's call it t, I want the durations for all the machines to be less than equal to t. But I don't know what t is. I want to make t as small as possible. One thing that's nice about this is by adding one more variable, t, you've changed this objective from a double, from a min-max to just a min. And that can turn out to be a good thing. So this is just to illustrate that there is not necessarily a single way to do an optimization. There could be multiple ways to do it from a given problem. How you do it is a mixture of creativity and your instincts and your knowledge of the landscape of different kinds of optimization problems. These two will not look different to you if you didn't already know that, hey, a min-max seems like a difficult thing to work with. Let's try to make it to a min. Otherwise, why would you care? It's all the same thing. It seems worse if you have one extra variable. Okay, so this element of choice is what I want to emphasize here. That there are lots of design choices you will make, and those will have consequences. And so what we will learn is how to figure out what those consequences are, and which choices are good and which choices are bad. Okay. So let's take another problem, and a problem again that you're familiar with. So let's take the problem of matching. In, let's say, even a simple case, we'll do matching in a bipartite graph. Again, the goal here is find maximum. Let's make this even weighted. Find a maximum weight subset of disjoint edges. And my input is a graph, and vertices and edges. Well, in particular, it's a bipartite graph. So my graph consists of a left side, a right side, and edges between them. And a weight function that maps edges to real numbers, or assume positive numbers. This is my input. And I want to write this in the language of optimization. So this sort of more abstract, context-free language of optimization. So again, variables, objective, constraints. What did I do here?
it can be chosen the same way as the earlier problem. Like you will have xi, and that would be equal to 1 if you choose the ith edge, and that would be equal to 0 if you don't choose the ith edge.
Okay, so basically you want a variable that encodes the choice of an edge to be in your answer. So my first variable will be, let's say, call it xe, which is 1 if e is chosen. Okay? And 0 otherwise. What's my objective? If I write down xe, then I can write down what is my max weight, or how do I write down max weight subset in the language of these variables?
xe into wp.
That's the weight contribution for one edge.
One edge, summation over all the.
So the objective is to maximize summation of we x over all edges in the graph. This x looks like a multiplication sign, which is not. Okay. What are the constraints? Do we have any constraints? What are my constraints? Yeah.
We have that same or similar constraint as previously, where we were looking for one-to-one matchings. So the number of vertices, or the sum of that xe value should be 1 for all vertices.
So how would I write that? So how do I write that constraint? Some of the xe value should be 1 for all. What does that mean? I think we need more information. I don't think you mean the sum of all xe is 1. You mean something different.
Right.
The sum of all the edges going from one vertex in U to all the vertex in V should be 1.
Okay. So sounds like what you're saying is for every vertex u, right, on the left side, right, the sum over all e that looks like u comma v xe should be equal to 1. And you might have to do something similar for v. Maybe there's a way to write this without having to put two separate constraints. Oh, maybe we'll do. So all edges going out. So now we have variables, objectives, and we have constraints. Right? And our goal is to find a maximum matching. Okay? So again, we have to show that if we in fact had a maximum matching, max weight matching in the graph, you will get an appropriate solution here. And if you get an appropriate solution here, you will have a max weight matching in the graph. Okay? Okay. So suppose we have a max weight matching in the graph, then for each edge that is picked, we set xe equal to 1. The objective is clearly the weight of all those edges, so that gives you the correct objective. I mean, the objective value is the same value. And clearly for every, this is true because these are disjoint edges. We have picked disjoint edges, so this must be true, this must be true, and we're happy. So given, one second, so given this, you will have no problem getting an objective on. Let's look at the other way around. Suppose I run this and I get some answer. Okay, all some values of xe are set to 1, right? I want to claim that this gives me a matching of a certain size. Right? So clearly, if I'm able to produce XE values appropriately, I will in fact get a matching. This satisfies all the constraints. But suppose this doesn't. Is there a possibility here that you could fail to produce an answer here for a graph where you should have been able to produce a matching? So let me give you a graph. What is the max weight matching in this graph? It has value 5, right? Pick that one edge label 2 and edge label 3. If you translate this in optimization, will you actually be able to get an answer? Try running your optimization without knowing where the graph, what the skull came from. You just have these variables and you have these edges set up, and you try to run this. What I want you to focus your attention on is, look at this constraint. Put that one there.
That's not one.
Huh?
That's not good.
Well, okay. First, I want to make sure all of you see the problem. The way we've set up the constraints for this problem, the optimization may not be able to produce any answer at all. Because there's no way to guarantee that for each vertex on the right side, you can guarantee that this is basically saying there has to be an edge coming in. These constraints have said every vertex has to be part of the matching. That's a very strong constraint. That's not even required for a problem. That would give us something called a perfect matching. We don't need that for a problem. We're just trying to find the best matching possible. We're not trying to match everything. So our constraints have asked us to do too much. They're asking us to do something that we didn't really need to do. And so we're going to fail. This is not a valid optimization way to solve the maximum matching problem. It will fail to work. And one way to answer this question, well, this is because the number of vertices on the left and right are not the same. That's fine. But there should have been a better way to frame the objectives and it wouldn't matter. So how do we do that? What do we do? How do we fix this problem? Remember the intent of this constraint. The intent of this constraint is to say that, look, you don't want to pick two things. Right? So you can say it by saying it should be exactly one, or you can say something different. Because what you're saying is that if you pick something, you shouldn't pick another thing. The option of not picking anything at all was not allowed for you. How would you incorporate the idea that, well, maybe you could have just not picked anything at all? That's okay. Which this is ruling out. One way to do that is to replace these. Because now it's saying, look, the summation has to be at most 1. Either nothing touches this vertex, or if something does, that's the only one you get. Because all the variables are 1 or 0, either you get a 1 or you get a 0, nothing in between. Right? So either this vertex gets nothing touching it, or it gets one thing touching it, and that's it. And if you do that, that fixes this problem. Now you can say that any solution here can be translated to a solution up there. So I should be careful though. It was always the case that a solution here could be translated up there. The problem was the other way around. My earlier argument was wrong. Right? The fact that I had a solution here, it didn't mean I could find a solution here. That would give me the same thing. This is this problem. So when you do this optimization, you have to be very careful with your constraints to make sure you are in fact capturing the thing you want to capture, and you're not capturing too much. You're not capturing too little. If you capture too little information, you'll be able to get a much bigger answer here. Like if you drop all these constraints, you'll get answers that won't apply. If you put too much information, your answer here will be much less. It will not give you what you want in the case of a maximization. So these constraints have to be just right. And there is an art to choosing constraints. That's another thing. But the point I want to make here is that you have choices at your disposal. You can have choices to do things that are both correct. You can have choices that will actually make something wrong. So when you design your constraints, you have to be very careful. And so you are essentially encoding your ideas about the problem in a different language, the language of these constraints. All you have are variables. You have to pack all your domain knowledge about the problem into some function for these variables. These are linear constraints, but you can have more general constraints as well. I was going to do another example which has sort of a quadratic objective function, just to show you what that looks like. But we can defer that next time. Okay. So before we adjourn for today, any questions? Yeah.
One constraint, I don't think that because it's symmetry, like we don't know which is U, which is V. So if we apply it on every edge.
Yeah. Well, the thing is, the constraints have to be over vertices. So you could say, I guess, yeah. So what you could say is, for every, you need some more notation here. What you would say is, for every vertex, the sum of all the edge weights for edges incident on this vertex is 1, at most 1. So what I would say here is, I would say, very quickly, where you go, let, this is a standard notation, gamma v equal to the set of all u such that either u comma v belongs to E or v comma u belongs to E, right? Then for all u in u union v, the summation over all let's say this is all, sorry, this is why we have to be a little careful with this. Equal to the set of all u comma v belong to E, union set of all v comma u belong to E, right? Then this summation over all E belonging to gamma of u x E is less than equal to. So that's, you have to write a bit more carefully. Right? So the neighborhood set is the set of all edges coming out of the vertex. Then for all vertices, the sum of, if you look at the sum of all things coming out of it, that should be 1. Yeah.
So you converted the min max into the soft constraint by using the.
What is the soft constraint? Is it constraint? Those are things soft constraint.
So is there any techniques like standards which basically help you out in like converting, or you making your objective of that?
There are. They're not as easily codified. So, for example, if you can make your make your constraints linear, that's a good thing to do. If you can make your objective a single minimization or a single maximization, that's a good thing to do. And for min and max, that's a standard trick. It works both ways. There are other tricks, like for example, if you have a constraint that's like the absolute value is less than or equal to something, then it becomes 2 constraints. As we've seen, so one is A is less than B, one is minus A is less than minus B, that kind of thing. So there are tricks like this you learn along the way. Is there like a rule book, a formula? Not quite. It's still a bit of an art. But there are some things you can system. Okay, we're running out of time, so I'll stop there. And we'll continue on.